So number 13, a 0.025 kilogram penny is dropped from the top of a 381 meter tall Empire State Building. Question 1, how much potential energy does it have? So potential energy is mass times gravity times height. So the mass of the penny is 0.025. The G is 9.8, and the height is 381 meters. So we can crank that out. Times 381 multiply 0.025 to get 93.3 joules of potential. Part B, if it is falling down at a speed of 30, how much kinetic energy does it have? This is just another practice. 1/2 mv squared. So 1/2 0.025 times the speed is, what did I say, 30 meters per second squared. So we have 900, 50 times 1.5, which is 11.25 joules. Question, or part C, when will all of the potential energy be converted to kinetic? So remember, as it is falling down, it is losing potential, just like the plane in problem 12. It is losing potential because it's getting closer to the ground. But it is speeding up, so it's increasing in the kinetic energy. So all the potential will be converted to kinetic when it's at the ground. If we were to draw, so up here the penny has lots and lots of potential energy, but no kinetic yet because it's not moving. And as it falls, it's faster and faster and faster, so that down here, right before it hits the ground, there's no potential energy left, because all of that potential has been converted to kinetic. So part C, all potential energy is converted to kinetic whenever it's at the ground, whenever it hits the ground. I'm trying to say that. How much kinetic energy will it have then? Well, if it had at the top 93.3 joules of potential energy, then when it's at the bottom, if there's no more potential energy, it's all kinetic energy. That means it has to have 93.3 joules of kinetic energy at the bottom. On part D says, how fast will the penny be moving when it hits the ground? So we can relate speed to the kinetic energy it has, once again with 1/2 mv squared, and we're just solving for velocity in this case. So you multiply both sides by 2, divide by m, and you take the square root. Such that square root of 2 times the kinetic energy, so 2 times 93.3 joules divided by 0.025 kilograms gives us, I believe it's 86. I give this problem every year, and it's always the same, because I use real numbers. The Empire State Building really is 381 meters tall. So 86.4 meters per second. Number 14, what two factors does gravitational potential energy depend on? We've talked about that. Depends on mass. The more mass anything has, the more energy it has in general. It depends on G itself, because the stronger the pull of gravity is, the more potential it has to fall with more speed, or with more energy, you can say. So technically, if you looked at, if the Empire State Building was on Jupiter, the gravitational pull on Jupiter is more, and so the penny would have more potential energy on top of the Empire State Building if it was in Jupiter. So. And finally, mostly it depends on how high it is off the ground. The higher it is, the more potential it has. Number 15, mechanical energy is basically the combination of kinetic and potential. And mechanical energy is conserved unless energy is lost in the system. In general, mechanical energy is always conserved in an isolated system. It means that there's no outside forces on it. Gravitational force. 16. What does the gravitational force between two objects depend on? Two things it depends on. First off, it depends on the masses of the two objects. So mass attracts, mass has a gravitational force, basically. Anything that has a mass attracts you to it. Something that we don't really know why it happens. There's actually some really interesting stuff going on right now where they've almost found the Higgs boson or this and that, which may explain what mass is. But for some reason, mass attracts things to it. So you are attracted to the pencil in your hand, or the computer that you're watching. There is an attraction between you and that computer because it has a mass. So, so the first thing that depends on is the masses of whatever the two objects are. And secondly, it depends on how far apart they are. So, and you can think of it as like Earth and yourself. If you are on Earth, yeah, you feel the gravitational force, awesome. If you go further away from Earth, if you go really, really far away from Earth, you're not going to be able to feel the force as much. Eventually you can go so far that you won't even feel that Earth couldn't even keep you down anymore. You would just keep on floating away. Alright. Yeah, you can just leave it at that. So masses and the distance. And that's given Newton's law of gravitation. Is there gravity in space? Yes or no? Absolutely. Gravity in space. It's just not as much. Alright. So I got the Earth. Talk about this for sure. You got the moon. Well, what keeps the moon orbiting around the Earth? ... Well, it's gravity. Gravity keeps the moon orbiting around the Earth. So clearly, there must be some gravity in space, or else that couldn't happen. So remember, gravity is a field force. We go around the sun because gravity pulls us toward the sun. So the gravitational force of the sun is spread out in all directions around the sun, such that it's like an invisible force that exists that is attracting us to the sun. So there's definitely gravity in space. Some places in space you may be so far away from everything that you might not feel any gravity, but it is in space in some places. And technically, you may feel a very, very small amount. You just don't feel it. If we wanted to calculate the force, like in number 18, where we're trying to find the gravitational force between the sun and the Earth, or Newton's law of gravitation. So G is 6.67 times 10 to the negative 11th, multiplied by the mass of the sun, multiplied by the mass of the Earth, 24, excuse me, divided by the distance squared. So the distance is about 150 million kilometers. So remember, we have to convert that to meters. So 1 kilometer is 1,000 meters. So there's an extra 1,000 meters in this. And what most students forget to do, it's common, not most, but it's a common mistake to forget to square it. So don't forget to square it. And even a lot of times students write it down squared, but then when they put it in their calculator, they forget to square it. So hopefully we can try not to do that. Times 5.97, e to the 24th, divided by 1. I guess I could put that in scientific notation. We should get 3.54 times 10 to the 22nd newtons. That's a lot of newtons, but it takes a lot of force to keep the mass of the Earth from floating off. So, what is the difference between mass and weight? Very important difference. Mass, everything has a mass. Basically, particles have mass, molecules have mass, so everything, paper is made up of molecules, so it has a mass. But weight is dependent upon the force that is pulling that mass. So weight is the gravitational force that pulls on something. it is possible to have mass but to be weightless. For instance, you are orbiting the Earth. The gravitational, technically, weight is the combination of the gravitational force and the normal force, such that yes, it's true that gravity acts on you, but you're weightless because there's nothing pushing you back up. So your feet don't feel don't feel any force. I think we mentioned that your weight, if you were to tape a scale to your feet, whatever that scale would read is your weight at all times. So that scale can change whenever you go in an elevator. Your weight temporarily changes because the elevator pushes up on your feet. So it would make that scale read a little bit higher. So your weight would increase. Of course, your mass does not increase unless you eat a really big burger when you're inside of that elevator. So mass is mass, mass is matter, and weight is the force on that. Yes. The gravitational. Actually, yeah, to be precise, this is the gravitational force, not just any force. Gravitational force. So how is it possible that astronauts orbiting Earth are weightless? We kind of just mentioned that. Remember whenever we did that, where we threw apples in class that day? And we kind of talked about how eventually you could throw it so hard that it would be going so fast that by the time the Earth curved around, the apple would have traveled so far that now when gravity pulls it down, it would still be the same distance from the surface of the Earth. So we kind of call it like falling around the Earth, where it's true that it's being pulled toward the center, but it's moving so fast this way that by the time it gets pulled down again, it's already moved to where Earth is curved. And so that's what astronauts in orbit are doing. Even though gravity is pulling the spaceship down to them, they are moving so fast, and there's no air resistance up there, so they can do this. They're moving so fast that they can that they're constantly falling. The apple is the humans inside of the spaceship, and even the spaceship itself, is constantly falling toward the Earth, and so it feels basically they're going skydiving with no air slowing them down, more or less. So they're constantly falling toward the Earth. It's just that the spaceship is falling with them, and they're going so fast laterally that they're falling, or that they're moving with the curvature of the Earth. So that's kind of how we do number 20. Where are we at? I have 2 more minutes. I'm going to have to stop this one. The next one should be pretty short, and it will be the last one.